Talk about Pascal's principle. And if you applied an external pressure to a liquid or fluid, and that applied pressure will transmit unchanged to every point within that fluid. So this principle actually we used in hydraulic lifts. So if you think about this hydraulic lift, if you apply a pressure, and the pressure you can write as force divided by area, and that pressure will transmit to every point within the fluid. So the pressure applied at this end will transmit to the other end of the fluid. So it will transmit unchanged to every point within the fluid. So the pressure is given by force divided by area. So if you have two different area, cross-sectional area over here, so you can use it as a hydraulic lifts. So in the hydraulic lift, what you do, like you have filled with a liquid over here, and it's filled with complete liquid, and you can see the area is the cross-sectional area at this end and the cross-sectional area at this end are different, and the pressure is given by force divided by area. And here, with applying a smaller force for a smaller area, so you can transmit that force to lift a car. That means you can transmit it to a higher force. But the important part here, so if you move this end over here by d1 distance, so as the output you are getting a very less distance, but still you can create very high force, but the distance is less. So we use this principle in hydraulic lift. Okay, let's work on an example here. To inspect a 21,000 Newton truck, a mechanic raises it with a hydraulic lift. If the radius of the smaller piston is 4.5 centimeters and the radius of the large piston is 18 centimeters, find the force that must be exerted on the small piston to lift the truck. Okay, so we have to lift a 21,000 Newton truck. Okay, and at this end the A1 area refers to the radius of 4.5 centimeters. So you have to convert the radius into area, and the larger portion area refers to 18 centimeters radius. Again, you have to convert that into area. The radius you have to convert into area. Okay, so we have to find the force that you exerted on the smaller portion. So you have to find the F1 force. If you use the Pascal's principle says if you apply a pressure onto the liquid, it will transmit to every point in the liquid. So if you apply a pressure over at this end, so that pressure will transmit to the other end. And the pressure is given by force divided by area. So let's say the pressure applied on the smaller end is equals to F1 over A1, and that is equals to the pressure created, the same pressure on the other end, that is F2 over A2. Okay, in this case the only unknown quantity is F1, so F1 equals to the F2 times A1 divided by A2. Okay, now you can substitute the numbers. So the force at F2, that is the weight of the truck, is 21,000 Newton, and the area at A1, so we have given the radius as 4.5 centimeters. So if you have radius, you can use pi r squared equation to calculate the area. So the area is pi multiplied by r squared, the radius is squared. You have to convert the 4.5 into centimeters into meters. So that will be 0.045 meters, and you have to get the square of that value divided by again pi. The radius is 18 centimeters, that means 0.18 meters square. Okay, and now you can simplify this expression, and you can find the force that you should apply at F1 end. It will be equals to 1300 newtons. So you can see once you apply 1300 newton at F1 at this end over here, so you can lift this truck or the car, which is 21,000. Okay, now we're going to talk about the Archimedes principle and buoyancy. So if you think about a fluid container, so the inside pressure increases with the depth, which will lead to a net upward force on objects inside there. So we call this the upward force as the buoyant force. And the Archimedes principle states that an object immersed in a fluid experience an upward force, that is the buoyant force, and this buoyant force is equals to the weight of the fluid displaced by that object. So again, so the weight of the fluid displaced by the object equal to the buoyant force. So that is the Archimedes principle. So we will talk about this Archimedes principle in next slide in detail. To explain the Archimedes principle, I will use this picture over here. So we have a cube, then one side of the cube equals to the length L, and this cube is completely immersed in a liquid, let's say in a fluid, and the fluid density is rho. And if you think about this liquid, so the area, the top area over here on this cube experiences a force F1, and in the same way, if you look at the area, bottom area, this part, it experiences a force F2. So we can calculate this F1 and F2 forces using the relation for the pressure. The pressure is given by force divided by the cross-sectional area, or the area related to that force. And simply you can say F1 force equals to the pressure at that point, P1 multiplied by the area. So here the area in the cube, so the side is L distance, so the area is given by L square, so that is the area. And similarly we can write F2 force. F2 force actually depends on the height of the liquid above this part plus the F1 force. Okay, so that means if I write expression P2 times area, the P2 value depends on the P1 pressure plus the height is, let's say this part is L, so the total pressure adds up to the rho, the density of the liquid, GL, and that multiplied by the area, again the area equals to L square. So you can simplify this expression a little bit, and you can rewrite this as P1 L squared plus rho G L cube. So this is the F2 force. And if you look at the force difference between F2 and F1, so that is equals to the buoyancy force. So the buoyancy force, I will write F buoyancy, FB equals to the force F2 minus force F1. Okay, so if I simplify this one a little bit, so the F2 is P1 L squared plus rho G L cube and minus F1 equals to P1 L squared. So you can see this term and this term cancels out, and finally you will get an expression for the buoyancy force as FB equals to rho G L cube. So if you look at the terms here, rho is the density of the liquid, G is the gravitational acceleration constant, and L cube is the volume of this cube. So in the same way, if you think this is the volume of excess water due to the submersion of this cube. So this is the volume. So we can replace this by the volume. Okay, so the Archimedes principle says the upward force or the buoyancy force equals to the weight of the liquid displaced by the object. So the weight of the liquid displaced by the object. So what is weight? If I write over here, so the weight is given by mass times gravitational acceleration constant. Okay, here what is the mass? Mass is the density times volume. Yes, rho V and multiplied by G. So here rho is the density and V is the volume. And we have the same expression over here. The buoyancy force equals to rho G and also volume. So instead of volume here we have L cube. L cube is again volume. So that means the buoyancy principle, if you want to write as expression, we can always write the force, buoyancy force equals rho density of the liquid, gravitational acceleration constant times volume. So this is the Archimedes principle. Now we're going to work on an example for Archimedes principle. Actually here we're going to talk about a specific case here, complete submersion. So a person who weighs 720 newtons in air is lowered into tank of water to about chin level. He sits in a harness of negligible mass suspended from a scale that reads his apparent weight. He now exhales as much as air as possible and dunks his head underwater, submerging his entire body. So if the apparent weight while submerged is 34.3 Newton, so the part A is find his volume and the part B is find his density. So we can make a small sketch onto this one. So the person is sitting on harness and we have a hanging scale there. So this scale reads, so when he is sitting on this harness and inside the water, so this scale reads his apparent weight. Okay, so the apparent weight is given as 34.3 Newton. And this person actually weighs outside the tank 720 Newtons. We have to find the volume. So if you make a free body diagram for this person's forces, so what are the forces? So we have the weight of this person, W, and we have upward force. One upward force is the buoyant force that rises due to the Archimedes law, the buoyant force. And also this scale reads some number, that means he got his apparent weight. So I will write this apparent weight as WA. And is there any other forces? No. the system in balance. So we have weight of the person, the buoyant force upward, as well as the apparent weight upward. And we can write a Newton's second law for this person's forces. So the Newton's second law says force equals mass times acceleration. But in this case, this person is at rest. That means the forces are in balance, no acceleration. So we can write the Newton's second law for this person. Let's say I will consider all the forces going upward as positive. So the apparent weight is a positive number and buoyant force is a positive number minus his weight is a negative number. And since this person is at rest, no acceleration, that means it equals to 0. Okay. And if you remember from the last slide, the buoyant force FB we can write as rho, the density of the liquid. Here he is in a water tank, so the density of water multiplied by g, gravitational acceleration constant, and volume of the person. So that is the water level, or that is the excess water level he got displaced by this person. So it's the volume of the person. So I will write volume of person. I will write Vp. And we can substitute this FB value onto this equation, and we can rewrite this equation as WA plus rho water G volume of the person minus person's weight equals to 0. And if you look at the values over here, so the apparent weight is given, the volume, the density of water is a known quantity, the gravitational acceleration is a known quantity, and the weight of the person outside the tank is given. So the only unknown quantity is the volume of the person. So we can calculate the volume of the person from this expression. So I will rewrite this expression as to get the volume of the by taking volume of the person into one side, the weight minus apparent weight divided by, here we have rho water multiplied by gravitational acceleration constant. Okay, now we can substitute the values to calculate Vp value. So since I don't have space here, so I will move to the next slide. Okay, again, if I write the expression here, the volume of the person equals weight minus apparent weight divided by rho water, density of water, multiplied by gravitational acceleration constant, and I can substitute the numbers here. So the weight of the person is 720 newtons minus the apparent weight is 34.3 newton divided by the density of water 1000 kilograms per cubic meter and multiplied by the gravitational acceleration constant 9.81 meters per second. Okay, now we can simplify this one to find the volume of the person. It will be 6.99 into 10 to the power negative 2 cubic meters. So this is the volume of the person. In the part B is asking what is his density. So we have to find the density of the person. And if I write the weight equals mass times gravitational acceleration constant. Okay. And the mass is given by, so if I write the density equation, the density equals mass divided by, so I will use the similar notation. So the density equals mass divided by volume. Okay, and this the density is mass divided volume, and we can get the mass from this equation, that is density multiplied by the volume. So we can substitute this m value into this equation here, and the weight of the person equals rho, that is the density. And what is this density actually? So the density of the person, and V is again volume of the person, okay, and multiplied by G, gravitational acceleration constant. So if you look at this expression, the weight of the person is given outside the tank, and we just calculate the volume of the person, and we know this is a constant. So the only unknown quantity is the density of the person, rho p. So you can write this rho p value as W over Vp into G. So you can substitute the numbers. Weight of the person is 720 newtons. Divide by the volume of the person. That's the answer for the first part of the question. 6.99 into 10 to the power negative 2 cubic meters. So here the cubic part is missing, so I will put it here. So the cubic meters, yeah, and multiplied by the gravitational acceleration constant, 9.81 meters per second. Okay, now you can simplify this one to find the density of the person. It will be 1050 kilograms per cubic meter. So this is the density of this person. Okay, the flotation is another special case of Archimedes principle. So if you consider this picture over here, so we have an object floats on a fluid, okay, and you can, as you see here, so this part of the object, so this part is only submerged in the fluid, and this is the only volume displaced by this object. So this, when it's floating, this is the only part displaced by this object. And if you measure the weight of the displaced amount of fluid, okay, so this weight is equals to the weight of the object. So let's say the weight of the object, this is the object weight W, and this is the liquid displaced, okay. So these two weights are equal. So you can prove this one from the Archimedes principle, but I'm not going to prove that one. But as a note, I would say, so when some objects are floating on fluid, so the displaced amount of fluid, and if you measure the weight of that part, it's equals to the weight of the object. Okay, here I'm going to talk about Bernoulli's equation and Bernoulli's principle in brief. So the Bernoulli equation gives the relationship between the pressure of the fluid and its speed and height, and you can get the relationship for two different setups. Let's say the initial setup and the final setup. So that means we are talking about the energy conservation of fluids. So actually Bernoulli equation gives you the relationship of energy conservation which is applies to the fluids. Here I'm not going to prove this equation, but I will, let's try to understand the terms of the Bernoulli's equation. So if you look at the first part of the equation, so we have P1. So this P refers to the pressure, and if you have a pressure in a fluid, so there will be an energy created due to that pressure. So this is the energy due to the pressure of the liquid. And the second term over here, 1/2 rho V1 squared. So here the V is the speed of the liquid, how fast it flow. So you can think a picture like this. Let's say we have a tube, water tube like this, and so it's moves like this one. Okay, and let's say we can measure the this is the ground level or the potential energy, 0 level, and let's say at this point this is it height y1, and over here the height is y2. Okay, and the water is flowing with the speed of v1 over here. So I will try it in different way. So v1, and over here the speed of the liquid is v2. Okay, and the density remains as constant, the density of the fluid over here, rho. Okay, and this is the P1 pressure at this point, and we have P2 pressure at this point. Okay, so if you think in this way, so we can refer the second term over here, that is the kinetic energy of the liquid flowing through this part. So if you take the cross section over here, so that is the kinetic energy on this part. And the last term over here, this is refers to the potential energy. So if you look at the height y1 from the potential energy 0 level, this is refers to the potential energy of the fluid. So this part refers to the first term of these equations, and the rest of the equation refers to the second part we are talking over here. So the P2 is the pressure at this other end, and 1/2 rho V2 squared equals to the kinetic energy at this over here, and the potential energy at this point also given by rho G Y2. Y2 is the height over here. So this is refers to the Bernoulli's equation again, and this is a equation for the statement of energy conservation. So the Bernoulli's principle has lots of applications, and one of them is airplane wing. So if you think about the shape of the airplane wing, so it designed so that the airflow more rapidly goes at the top of the airplane, and the bottom of the airplane the airflow is slow. Okay, so when you have higher faster airflow, so what it will happen, so the pressure will be less at the top part. So you have the faster airflow, the rapid airflow. Due to that, the pressure at that point is lower. So when you have lower pressure at top of the wing and the higher pressure at the bottom of the wing, what it will happen, it will create a lift. We call this as aerodynamic lift. So the pressure over here, let's say P1, and the pressure over here P2. So the P1 value is less than P2. So the bottom is high pressure, the top is low pressure. So we always know the pressure flows from high pressure to the low pressure. That means it will create an upward lift force. So that is the aerodynamic lift. So this is one application of airplane, the Bernoulli's principle. So you can find many applications like this, and probably we'll talk one more application in next slide. Actually, this is not an application. Actually, this happens due to the Bernoulli's principle. So let's look at this example. During a hurricane, 42.6 meters per second wind blows across the flat roof of a small house. So we have a flat roof over here, and at the top the airflow is 42.6 meters per second. It has the speed of 42.6 meters per second, and find the difference in pressure between the air inside home and the air just above the roof. So we have to find the pressure difference. So if you look at this picture, so you can see, so when you have hurricane, the airflow is only going through the top of the roof. And since the house is covered, so the bottom part of the roof, so we don't have a speed. And higher we have a speed. On the top of the roof we have a speed, but not the inside the house. The airflow is, the velocity is, or the speed is 0. So you can write the Bernoulli's expression. The Bernoulli's expression, if I write it over here, so it will be the pressure P1, okay, and plus 1/2 rho V1 squared plus rho G height. Let's say the height from the ground is y. So here I'm considering this level, and let's say this height is y, okay, from the ground level, and equals to the second part. So it will be P2 pressure 1/2 rho V2. So this is the speed V2 plus rho G y. Here the rho is the density of the air, and V1 is the speed at the bottom of the roof, and V2 is the speed of the top of the roof. And if you look at this expression, so the potential energy term equals to the initial and final. Both potential energies are equal, so we can cancel out this term, okay, since they are equal. And if you rewrite the other part, and what is the V1 speed? V1 speed is 0, so this term we can consider as 0. So since the V1 is 0, this term will become 0. And we need to find the pressure between air inside home and air outside home. So we need to find the pressure difference, P1 and P2 minus. So the difference, so I will write P1 minus P2 is the answer that we need, and I can rewrite the other part of the equation, that equals to 1/2 rho V2 squared. So that is the equation we need to solve. So if I substitute the numbers, 1/2 rho is the density of the air, that is given as 1.29 kilograms per cubic meter, multiplied by the speed of the wind, so it's given as 42.6 meters per second, and here actually we have to take the square of that value. So that will be, so if you solve this one, so that will give you the pressure difference between the inside the home and just above the roof. So the answer is 1.17 into 10 to the power 3 pascals, or you can write in the other unit kilopascal. So this is the answer, the pressure difference between that. So if you have higher pressure difference, let's say this pressure is higher than, like it's enough to lift the roof, so the roof will flow due to this wind, so it will blow out due to the wind. So this is this phenomenon happened due to the Bernoulli's principle.